So today, we're going to dive into a pretty compelling and definitely controversial new theory in developmental science. It's called the Acetaminophen Hypothesis.
And it all boils down to this one huge question. Could something as incredibly common as acetaminophen, the stuff in Tylenol and countless other products, actually have unintended effects on a developing brain?
Okay, so here's the core idea in a nutshell. This hypothesis suggests a potential link between taking acetaminophen during pregnancy and a higher risk for conditions like autism spectrum disorder and ADHD. This is a massive area of research, and we're about to break down exactly what the science is suggesting.
So here's how we're going to tackle this. First, we'll cover the basics of the hypothesis itself. Then, we'll look at a key mechanism they call a cellular power failure. After that, we'll explore what it might do to the brain's protective shield, why males could be more vulnerable, and finally, we'll wrap it all up with what we actually know so far and what we don't.
All right, let's jump right in with the core of the theory.
The whole thing really hinges on this idea of a cellular power failure. You can think of this as the engine room for the entire developing brain. If something goes wrong in here, well, it can affect the whole system. And it all kicks off with one very specific chemical byproduct. And that byproduct has a name, NAPQ. When your body breaks down acetaminophen, it creates this stuff. Now, normally, our bodies are absolutely fantastic at neutralizing it and getting rid of it, no problem. The theory, though, suggests that under certain conditions, that whole cleanup process might get overwhelmed.
And this is where we see this potential domino effect. First, NAPQ starts to build up. Why? Well, pregnancy itself can sometimes lower the body's supply of a master antioxidant called glutathione, which is exactly what's needed to fight NAPQ. Second, when NAPQ isn't cleared out, it creates what's called oxidative stress. You can think of it like cellular rust, and it starts damaging the cell's power plants, the mitochondria. And the final step? A full-on energy failure. Those damaged mitochondria just can't pump out enough fuel for a super high-energy organ like the developing brain.
So if the brain's power grid is down, what happens? Well, the potential consequences line up with traits we see in some neurodevelopmental conditions. We're talking about things like impaired development, which could show up as challenges with social communication or repetitive behaviors. It's also been linked to attention issues, like an ADHD, and even something called neural fatigue, where brain cells literally run out of steam.
Now look, this isn't just some idea floating out there in the ether. Other research has already shown a really strong connection between ASD and problems with mitochondria. The question is, just how strong is that connection? Up to 80%. Yeah, that's a staggering number, right? The fact that up to 80% of kids with ASD already show signs of mitochondrial dysfunction is a huge reason this hypothesis is getting so much attention. It's proposing a possible environmental trigger for a biological link we already know exists. Okay, so we have this cellular power failure, but that's just one piece of the puzzle. The theory suggests there's another layer to this, a potential problem with the brain's main line of defense. And that defense system is the blood-brain barrier, or BBB for short. It's this super dense network of cells that acts like a high-security bouncer for the brain. It's incredibly picky about what it lets in and what it keeps out, all to maintain the perfect, stable environment for our neurons to do their job. But here's the thing, that shield isn't invincible. And if you look at what can weaken it, well, this is all going to sound pretty familiar. That same oxidative stress we just talked about can damage the gatekeeper proteins of the barrier. Inflammation can make the whole thing more porous, and crucially, that mitochondrial dysfunction starves the barrier of the energy it needs to power its own defenses. So the bottom line here is pretty clear. A leaky or weakened blood-brain barrier in a developing fetus could be a really big deal. It essentially opens the floodgates, letting harmful things like NAPQI itself or other inflammatory stuff get into the brain during its most critical growth period.
This brings us to what might be the most fascinating and definitely the most complex part of this entire hypothesis. It actually tries to provide a potential explanation for something we've observed for a very long time.
I mean, we all know that ASD is diagnosed way more often in boys than in girls. It's nearly 4-to-1. So why is that? Well, the acetaminophen hypothesis suggests the answer might actually be found in some fundamental biological differences in how the male and female brain develop, specifically that protective shield.
Now, based on what we've seen mostly in animal models, there seem to be some key differences here.
Hormones seem to play a role. Estrogen in females is thought to actually make the barrier stronger, while testosterone in males might make it a bit more permeable. When it comes to kicking toxins out, the female BBB seems to be more efficient, and in response to stress or inflammation, the male brain might have a bigger, more damaging reaction.
So what does this all add up to? Well, the theory proposes that males could be more vulnerable for a few reasons. Their blood-brain barrier might mature a bit slower, they may naturally have lower levels of that key antioxidant glutathione, and their mitochondria might just be less resilient to stress to begin with.
Okay, we've just gone through the whole intricate theory, right? But now we absolutely have to take a step back and put all of this into its proper scientific context.
And this right here is probably the single most important thing to remember from this whole explainer. What we've been talking about is a hypothesis. It's a really interesting logical framework that connects a lot of dots, but it is not a proven conclusion.
We have to be really honest about the limitations here. A lot of this data comes from animal models, not people. And in human studies, it's incredibly hard to separate the effect of acetaminophen from, say, the fever it was taken for, or from a person's genetics. Plus, measuring the blood-brain barrier in a human fetus, yeah, that's extremely difficult to say the least. And let's not forget, ASD is a really complex condition with many, many different factors at play.
But that doesn't mean this hypothesis isn't valuable. It absolutely is. It might not be a final answer, but it's like a roadmap. It gives scientists clear, testable ideas to explore as they research prenatal health, medication safety, and the true origins of neurodevelopmental conditions.
And that really leaves us with a final big question to think about. As this kind of research moves forward and we learn more and more about the incredibly delicate environment of the developing brain, how might all of this one day change the advice we give to ensure the healthiest possible start to a new life? Thanks for joining me for this explainer.